what we'll do is we will finish off the structural part. So yesterday we looked at all these properties, like degree distribution, path length, and so on. And then we did some things on the centrality, right? So which are the important nodes in the network. And then the page rank and the hits are the sort of the two of the most popular ways of analyzing the sort of some scores that we compute, some ranking functions we compute, things like authority, hub scores, prestige, so all those things are essentially related. And what we found out is actually that the core idea, right, is this notion of the eigenvalue, eigenvector computation. It's an iterative matrix vector multiplication problem. So the matrix here is the adjacency matrix of the graph, and it's an extremely sparse matrix, right, because there are very few connections from any given node to any other node. So there are only a limited number of connections. So in principle, this computation can be done very fast because it's a very sparse network, and the sparse matrix vector multiplication can be done, much faster than what we would do with a dense matrix. So that's where we left off, and what I want to do today is to look at the actual sort of the modeling part. So this is, we were trying to see, in terms of real-world networks that we observe in the social networks, in the biological networks, and in many other, food webs, ecological webs, and so on. How do they actually differ from random graphs? And so we'll try to sort of look at some of the basic models for that to finish off this sort of structural analysis part. So one of the key properties of real-world networks is the small world property, right? So I mentioned this last time, this chain letter idea that we all connected with, very few connections. And so mathematically, what does that mean? So mathematically, what that means is that, you have n number of nodes, n can be billions, right? And so the question is that what is the diameter of that graph, or what is the average path length? And so this mu L is the average path length. So that's one way of sort of characterizing, what we mean by a small world. So this is the average path length. So mu L is the average path length. And if that is logarithmic in the size, in the number of nodes, then we can say that the network is essentially a small world network. So even if you have a billion nodes, you have about 6, connectivity. In fact, sometimes the networks are even much smaller than that. The connectivity can be what is known as ultra small world. So it could be much smaller than even log n. For example, it could be log of log n. So it's a double logarithm. So in other words, this is something that we observe. Now, once you observe something, the question is, why does this happen, right? So what might be the explanation? So I guess that's what we're trying to essentially get at, is that we observe something, and then we would like to see, okay, what are the generative process? What might have caused this kind of behavior to emerge? So it turns out that actually this is a very simple property to, in fact, replicate. Because even random graphs happen to be small worlds, as we'll see. So this is not a very hard property to actually, so it just turns out that if you just even put random connections between people, it will ultimately turn out to be a small world network. So randomness in some sense is the key. And we'll see that so in other words, explanation is as simple as that even if you just put things pretty much blindly, with some probability, the network will end up being a small world network. On the other hand, actually, if you design a network, sometimes it can be a large world network. Sometimes it can have big diameters. And we'll see an example of that also. The other key property that we were trying to elucidate last time is actually the degree distribution, right? So we said that, and this is one of the key reasons, in fact, where people saw the first difference between the random graph and the real world networks. And we'll see, we'll first analyze the random graph shortly. But the real world networks they exhibit the scale-free behavior for the degree distribution and other things. But essentially what this leads to is this notion of a power law. So the key point is that f of k, if you remember, is the probability of seeing a vertex with degree k, right? So that's our probability distribution, our probability mass function. And so what this says is that this degree, this probability, tends to be proportional to the degree to raised to some power. So this gamma is the key point here, that the probability of seeing a given edge, seeing a given node of a particular degree is proportional to k to the minus gamma. And this minus gamma will change. So for different networks, that's a constant normally that we want to estimate. And so that gamma can be minus 2, minus 3, minus 1.5. So it's a negative slope. And what this, so if you put a, if you just think about this for a minute, what this means is actually it's 1 over k to the power gamma, right? So what that says is that if your degree is small, okay, if your degree is small, then you have a relatively high probability of being seen, right?
Yes.
And if your degree is extremely large, so it's very large, then obviously the probability is going to be low. But there'll be many. So what we observe is that there are lots and lots of nodes with very small degrees, which will come out of this, and there are many nodes. And there are a few sort of these hub nodes with extremely large, probabilities, and they will also be observed from this. Now, one of the key things about this power law is that how do you observe it, right? So if I were to just do a plot, right? So there is a sort of a mass function, and what is the relationship? So you have obviously lots and lots of nodes. So we want to look at the relationship that power law, because of the way the relationship holds. If you actually take the logarithm on both sides, you get the log of the probability, is log of that alpha times, so alpha is some constant, right? It's the proportionality constant. We don't really care about the alpha too much. Is the k, so I've basically turned that proportionality into an equation. So alpha is some constant for that proportionality, we don't care. K minus gamma, right? And then I can break that up. So that would be essentially, log of alpha plus log of k to the power minus gamma, and then the minus gamma I can pull out. So that will become log of the probability is minus gamma times log k plus some logarithmic term. Now this equation is, why we did it this way is that because this one is our y variable, this is our x variable, this is some offset, and this gamma is actually the slope, right? So the clearest or the easiest way to observe a power law is first to plot the degree distribution, right? So you basically plot k versus log k versus log of the probability. So we plot the log k here, and we plot the log of the f of k here. And then if you observe a negative slope, a straight line, then that's a clear indication of a power law behavior. So that's a very easy way to sort of visually check. And this is also how you fit the data actually. So if I give you a real world network, so extremely large, let's say social network, you can in fact plot the degree distributions. And then of course you may not know the slope. So the idea is that you want to sort of reverse engineer and figure out what is the slope. So we do the best fitting line, and then we figure out what that slope parameter is. So that's essentially one of the key things is, if you want to describe a network, what's really happening is that you plot this log plot, the k versus the probability, and then you observe what happens. So here's an example of that. So this is an example of a real network. It's not a very large network. This is in fact the human. It's a subset of the human protein interaction graph. So there are millions of proteins and they interact with each other. This is a small subset of those. So there are about 10,000 proteins in this, about 37,000 edges. And then if you actually plot what the degree distribution looks like. So we have this log, the log plot. So on the x-axis, you can see it's the log of the degree. And so by the way, this means, it's log to the base 2. This is actually 2 to the 7. This is 2 to the 8, right? So there are some nodes with extremely high degrees. And then these are the probabilities, again, in the logarithmic scale. So now, forget this, black line, because that's something you have to estimate from the data. So all you see is these, dots that I've plotted. And now the point is that what is the trend, right? So we would like to sort of figure out how do these real-world networks behave. So this is more of, as I said, a reverse engineering problem, that what is the distribution? Is it a normal distribution? Is it Poisson? What kind of distribution can we use to characterize this? So the key thing here is that the data is not exactly a straight line, right? I mean, we can see that there is some, maybe it's more of, maybe a curve like that, right? So obviously the data is not going to be a perfect power law in that sense, because there are going to be regions of the space where it does not really fit that behavior. And we can also see something else, right? What we can see is that that there is a sort of a wider spread here than you would expect, right? So there is, why should that happen, right? So the point is that we are trying to simplify things. I mean, if you really wanted to explain each and every nuance of that network, right, you'd need a much more complex model. So the idea is that, is there a simple behavior? And for that simple behavior, normally what we do is we sort of chop out the, say if I wanted to do a best fitting line, I will not start at the lowest and go all the way to the highest. What you can do is you can say, okay, let's figure, just skip a few very small degree nodes. So I started fitting the line actually with degree 2 onwards. And I went up and I ignored even some of the data at the higher end, and maybe I stopped at 7. So the idea is that, you sort of trim. So I just want to get an estimate for, can I get a linear behavior in this trimmed, region? And that is fairly decent. I mean, so again, the question is that there are spaces of the distribution which may not be an exact fit, but the majority I can capture, and that happens to be a power law. In this case, this is an estimate. So this is the slope that I can estimate from the best fitting line. That is actually minus 2.1. So it at least indicates that yes, there is more or less a power law type of behavior, but there are more things happening than that. And so you might, one might be interested to see, explain this part of the space, what's really happening there. Why do we have so many nodes with high degree? And this you can explain, and this, in some sense you have to go to the biology now. You have to say, okay, that means we do see in a real biological network, right, a lot of these complexes. So because proteins form complexes, and so in other words, they are interacting with many other proteins, and so you see many of these sort of, very highly complex biochemical processes, and maybe that requires the cooperation of lots and lots of things, right? And we do know that that is true, right? So if you look at the DNA and how the ribosomal assembly sort of transcribes it, translates it, and makes a new protein, it's a very complex system, and there are many parts to it, and they all have to interact for some manifestation of a protein. So that makes sense. So, but that may not be true for some other networks. So in any case, the idea is that you try to understand and see what's happening. So power law degrees can be found out in that manner. Okay, so that's one thing. So in other words, the degree distributions have the scale-free or power law behavior. And then the third, so these are some of the initial properties, and then people have actually looked at many other properties since these, but these are some of the crucial ones. So the third thing we normally observe in real-world networks is the so-called clustering effect. So real-world networks are small worlds; they are power law or scale-free. And the third thing is there is this some sort of a clustering going on around each node. So remember we studied this thing called the clustering coefficient, right? So you can look at the clustering coefficient, and what we'll do is we'll break it down by degree now. So you say, if I look at a network, and I pick a node with a certain degree, let's say degree k, what is the clustering coefficient for the average clustering coefficient for all nodes of degree k? So let's say I'm interested in degree 5. So I'll say, okay, there are 100 nodes with degree 5. what is the clustering coefficient for all of those, and then what is the average value. So then we can plot that CK. So CK now is not the clustering coefficient for the entire graph, it's the clustering coefficient with respect to the degree. So CK says what is the clustering coefficient for nodes of degree K. And interestingly, this also turns out to be a power law. So many real-world networks, biological networks, social networks, they have power law clustering effects. In other words, there are going to be, there are going to be many nodes that are smaller, degree nodes, but they have a higher clustering coefficient. And obviously, but you do see also, a few of these sort of, again, the hub type of, nodes. So nodes with extremely high degree will obviously have less of a clustering effect. But sort of the mental picture you should have in mind is that it's kind of like, the spoke and the hub kind of a model, that many networks are kind of like, you have, so you have a high degree node, it connects to many, many things. So you don't expect to, see too many connections between the neighbors of this node. I mean, some of them might be connected, but each one of these might be connected to many other things, and then they tend to be highly connected to each other. So it's like these hub nodes link clusters together. So in a complex interaction, web, you have these sort of very smaller clusters here, and but the clusters generally do not talk to each other. Okay, they generally go through some other, some sort of a hub node to get to some other point. And this is kind of true also in biological networks. You have sort of these housekeeping genes that are normally always present, and they link these other, complex processes together. You can explain food webs, ecological webs. So this kind of behavior is actually observed in lots and lots of these, real-world networks. That you have this local clustering, and then you have these hub nodes that, connect different parts of the space, and again, it makes it a small world network. So these are just three properties. I mean, there are many other properties one can study, of course, right? And so people have looked at properties, what happens when the network is evolving, nodes are coming in and going out, so in time. So a good example of this, for example, study would be like the Wikipedia, right? So the good thing about the internet age is that we can essentially record everything. And so one can actually just rewind the clock. And so if you look, if you go back to the 2000s, early 2000s, late 90s, when Wikipedia was just coming up, there were only a few pages, and then, slowly and slowly that thing started to grow. So we can actually look at the entire history and then study what happened in time. How did this network expand? Same thing can be done for, Facebook. Initially, obviously, there were only few adopters, people switching over from other, MySpace and, other social networks. And then how did that expand? So they have all this historical data, so one can then go around and verify, what kind of behaviors do we see, and then how do we explain them, right? So obviously, we're trying to find out the explanation. But these are the key sort of, some of the very basic properties, and one can go much beyond depending on the application and what one is interested in. So, fine. So now we have these three things. They say, okay, real world networks are small world, they are power law of degrees, power law of clustering. How do we explain this? So let's start with the most simple model, which is this random network model, right? So because this is, the random network model is extremely important because anytime you want to do a statistical sort of, estimate, right, you would like to see what would happen under random chance. So that's the basis for hypothesis testing. So what you do is you say, here's my conjecture, here's my hypothesis that, so here's the statistic I'm computing. Let's say average path length is, what I observe is 10. So in other words, I have this extremely large network. Let's say it's the Amazon network of, who's buying what and, how the connections are. And let's say that I just computed statistics. The average path length of this network is 10. Fine. So what does that mean? Is that a good thing or a bad thing? What is the probability of observing that? So normally what you have to do is that if you want to get a statistical sort of, sort of confidence, right? So you have to say, is it statistically significant, right? So what you would do is you would say, okay, let me generate a random network which looks like the network I have, my real network. And then in this random network, now So first thing is that if I know the distribution, then I don't have to do any random generation. If I knew exactly how the path lengths would be distributed, right? So if I knew that the path lengths are normal, then it's easy to basically see where do you land up, right? So what you would do is, so basically the point is, so let's say you have this extremely large graph G, and from this graph you compute this statistic mu as, and it happens to be 10, right? So the question I want to know, what is the likelihood, or what is the probability of that happening? So if I knew that the degree distribution is normal, so supposing someone told me, by magic, or if I knew something about the domain, and if I know that the average path lengths are normally distributed, let's say with mean 1, let's say. No, I guess 1 would be too small. Let's say mean is 3. So if I knew that the mean of path lengths should be 3, and if I know the standard deviation, let's say, is 1, so if sigma is 1, so let's say sigma is equal to 1, then I know precisely, right, how many deviations away this value is. So 10 is, a certain number of deviations away, so I say 10 minus 3 divided by 1. So this is the z-score, right? So I can compute the z-score value, that is how many standard deviations, this is essentially the value that you observe, so let me actually call this x, or let's just call it L. So what we do is we say, this is the value I observed, here's the mean value divided by sigma, right? So that's your standard score, or the z-score, in terms of how many deviations are you away. So in this case, it would be actually 7 deviations away, which is extremely, extremely rare, right? It actually is in the tail end of the distribution, it's somewhere over here. That is, your value of 10 is extremely unlikely to be seen by random chance. Or under this distribution, we are not likely to see it. So if you know this, that's great, right? But what will happen is that for many real world statistics that we want to compute, we actually do not know the shape of the distribution. So I don't know whether it's normal, whether it's bimodal or whatever. So what should we do in that case, right? So in that case, what we do is we generate a random graph. We do a simulation, essentially, a permutation test. So you basically generate one random graph, you compute a value. You generate another random graph, you compute the value. A third random graph, a fourth, a fifth. You do this maybe 100 times or 1,000 times to get an estimate of what is the average distribution of the values. So in other words, each time we are generating a random graph and then testing it out, right? So random graphs play an extremely important role in that sense, that we need to have a null model. If you're going to do a statistical test and you want to know what the distribution might look like, you would probably want to have a random graph that we want to study. So anyway, it's a good thing to study. It's, and if you could explain the real world phenomena with random stuff, then we didn't really have to have other sophisticated models. Right? Is randomness enough to explain everything? So this is extremely popular, like I said, was a very important field in the 60s and 70s, and Erdos really, Paul Erdos, he's the guy who basically started this whole area. So the idea is that you give me two parameters. Okay, you tell me you want graphs with n nodes and m edges. Okay, so these are the two input parameters. So someone tells you, look at all the possible graphs with n nodes and m edges. So those are the two input parameters. And now I have to generate a random graph for you. And the random graph basically should be chosen equally. So any random, in the entire space of all the possible graphs of n nodes and m edges, I have to pick just one out of them. So I'm using this capital M to denote, so what we can turn this into sort of an edge selection problem. So we can say that, there are n nodes. So among those n nodes, there are obviously n choose 2 possible edges. So I'm going to call that the capital M. So I'm going to say this capital M is the space of all the possible edges that can be there. And out of that space of all the possible edges, I'm going to choose the small m. Right? So small m is the input parameter. So given the number of nodes, I know totally this is the maximum number of edges I could have had. If my density is 1, I'll have all the edges present. but I need to only select the small m. And so you can also think of this as the probability of an edge. So if I look at small p, which is the probability of an edge, that is simply the small m over big M. Right, because I'm selecting only a few number of edges out of all the possible number of edges. So P is called the success probability, and it's going to play a key role when we analyze, what the behavior of this network is. So the first question is, how do you generate a random graph? So, the naive way would be that you basically go through all the n choose 2 choices, right? And you can say, I'm going to select an edge with probability p and not keep it with probability 1 minus p. So I basically flip a random number. If the random number happens to be less than or equal to p, I keep the edge, otherwise I don't keep the edge. But this is of course extremely slow because you're going to do n squared computations, n squared processes. So actually a much faster way is to just do direct. What you do is you essentially at random pick one node, okay? And then randomly pick the endpoint for that. So you just have to do 2 random numbers, from 1 through n. And anytime you pick 2 numbers or 2 vertices rather, you can put the edge between them, if the edge is not already there. So this way, I mean, sometimes the edge, sometimes the edge may already be there to begin with, but that's okay. I can then repeat, So I repeat this process till I have exactly m edges. So the idea is that, this way we can do an extremely fast generation of the network. So the idea is that, basically think of these nodes as basically, here. So you start out with n nodes, n vertices, and now I have to generate, let's say, m equal to, I don't know, maybe 5 edges, right? So what you do is randomly choose one node. So I choose this node, okay? And now randomly pick another endpoint for that node. So maybe I choose this one and I just put an edge between it. So I've now generated one edge. Now the remaining edges is 4. So I repeat. I say, so the number to be, so I've basically done 1 and remaining 4, right? So this is remaining. Okay, so now let's say I repeat. But let's say just by chance, I happen to pick the same node and I happen to pick the same node. So this would be a failed trial, basically. If your two points end up being exactly in the same edges, so all we have to do is that if the edge is already there, then do not decrease this count. Right? So we just call that a failed trial and then repeat. Then again pick 2 other random nodes. I pick this, followed by this, I connect them. Pick this, followed by that, I connect them. If we happen to again choose one of them, just it's a failed trial and so on. So keep on going this way till you have exactly, well in this case I have 1, 2, 3, 4, and maybe the 5th one is this. So that's a random instance. And the good thing about this is that it only takes you more or less O of m steps, okay, times 2, because you're going to do 2 endpoints for that. And there might be a few failed trials, but if you look at the probability of failure, it's extremely small, right? I mean, I have a huge number of possibilities. The capital M is a number of possible choices, and the small m is extremely, generally very small. So the chance that you'll end up picking the same 2 endpoints is extremely rare. But even if it happens, it's not a big problem. So this is a very efficient way of generating the random graph. So anyway, we now have a good, clean and quick way of generating a random graph. And I already mentioned about the probability. So now the question is, okay, so now you have a way of generating a random graph, but what can you say about the degree distribution, right? So that's one of the key things we want to know. So let's look at that. So what about the degree distribution of a random graph? So actually this is extremely easy. You don't even have to do this whole, generation process. You can actually analyze this directly. This is one of those easy cases where actually we can figure out exactly what the shape looks like without even doing this simulation process. Because all you have to do is, if you look at a given node, so let's say I chose that as my starting point. So one node has been chosen, and now I have to look at the degree, right? So I'm interested in the degree of this node. So there are in there are n minus 1 choices. Right? So this has already been chosen, so I remove one. Already fixed one of the endpoints. So there are n minus 1 other choices for, and this node can connect to any one of those, right? And now I also know the probability of connecting to any one of those. The probability is fixed for the whole network. Any edge will appear with probability small p, right? Which is what we had from, so I know the probability of success, P is the small m over the big M. So that P is basically fixed. Once you tell me what the n is, what the small m is, I can compute this probability. And so actually this is just a very simple success or failure kind of a thing. All you have to do is, this node will connect to that with some probability, that probability of success is P. It may connect to that with also probability P. So each of this is actually what is known as a Bernoulli trial, right? It's just a 0-1, whether or not you're a success or a failure, and the probability of success is P. And so we're just repeating this n minus 1 times. So that gives us a binomial distribution. So it's actually a very well known, So this distribution is exactly going to be, you have n minus 1 choices, okay, out of which you want to select exactly k, right? So you're going to know what is the probability of degree k, that observing the degree k. So in other words, if I observe this, I observe this, I observe that, so it has degree 3 out of 7, right? So 7 choose 3 would be, 7 choose 3 would be the number of ways in which I can have, I could have chosen 3 of these edges. So it's n minus 1 choose k. That's the number of ways of choosing k endpoints out of those n minus 1. And then, of course, the probability of choosing those k is p to the power k, right? Each one of them, k of them, p times p, there are k of them, so p to the power k. And of not choosing them is the remaining, n minus 1 minus k. So that's our classic distribution. This is the binomial distribution. So in fact, as I said, this is a very neat way of looking at it, because I don't have to do any simulation, any generation. I can directly tell you what the degree distribution looks like. Okay, and then because this is a well-known distribution, I know exactly what the mean should be and what the variance should be. So in the binomial distribution, the mean or the expectation is simply the number of trials times the probability of success. So it's p minus 1 times p. And the variance is actually the number of trials times p, the probability of success times the probability of failure, which is 1 minus p. So that's the variance. So I know exactly now, in a random graph, what the degree distribution looks like. So this is true for any node in the graph. Rather, across the whole graph, we can make this statement. So that's very good. So then the question is that, is this a power law, right? So is the binomial distribution a power law? No, it's not a power law, because you can quickly do an estimation. So what you can do is you can say, what we are really interested in is very large networks, right? So we want to sort of approximate this binomial by putting in our assumption. The binomial distribution is an exact distribution. It satisfies all the conditions. But we want to get a little bit of an approximation when n goes to infinity. That means we have extremely large graph, right? So we just study what happens to the network when n goes high. And whenever n goes high, the probability of success will automatically go low, because we know that p is small m over n choose 2, right? So when n becomes extremely large, n choose 2 becomes even much larger, and the small m is just small number of things. So this will automatically go to 0. So we want to basically say when the probability of success is extremely small, and the graph is extremely large. Another way of saying this is that it's a very sparse network, right? This is a sparse graph. That is, the probability of having an edge is extremely low compared to the whole network. So that's what you really want to see in a real world network. They are large, they are sparse. So what happens? So then you can approximate the expectation is simply NP. So this n minus 1 versus n is of no consequence. N is extremely large. So the expectation simply becomes n times p. And the variance, interestingly, when p goes to 0, 1 minus p goes to 1. Okay, so 1 minus 0 is basically 1. So this also becomes NP. So now you have a case where your expectation and your variance is actually both the same. Okay, there's n times n is the number of nodes, p is the probability of success. And so we use this lambda. So I'm going to say lambda is this parameter np, and this is both the mean and the variance of the distribution. And actually, you can then approximate the binomial. So this is a well-known result that when n goes to infinity, p goes to 0, the binomial distribution can be approximated with a Poisson distribution. And I'm putting it in this shape so that we can look at the actual, relationships, right? So this is much clearer to see what is the relationship of the degree versus, so the degree appears here as a factorial, right? Everything, and also as a lambda to the k. So if you look at just the terms that involve k, they're very far from a power law. So in power law, what I want is f of k should be proportional to k to the minus gamma, right? That's the shape of a power law. And here we have something else. This is actually, if I rearrange this, let's not worry about e to the minus lambda. So actually, that's just some constant for us. It's actually lambda to the k. So that's completely different from that. And also it is k factorial. K factorial, you can do a little bit more, Stirling approximation and get a better idea, but it's basically, think of it as k to the power k. So it's actually going to be k to the power minus k. Okay. So it's going to be basically proportional to this number. So in fact, we don't even need to have that. So this value, right, is very far removed from the power law. And nothing, power law is actually an exponent. It's, this appears as the k to some power, negative power. Here it's actually k to minus k and also lambda to the k. So it's k appears as an exponent. So it's an extremely, completely different type of distribution. So we know now that random graphs are not able to explain social networks, biological networks that we see in the real world. So that means these graphs are not going to be adequate to describe many of these, especially the power, the hub nodes and those kinds of things. We don't really see them in random graphs. Okay, so what about the clustering effect? So is there any kind of clustering going on in these random graphs? So actually, if you look at this, if you look at the clustering coefficient for a node, if you remember, what we do is we compute, so here's a node, and you look at the neighbors. So this node is connected to all of them, right? Because they are the neighbors of this node. So now I want to know what is the clustering coefficient, and the clustering coefficient basically depends on how many of these nodes are connected. So what is so these red nodes versus the number of possible edges I could have had among my neighbors, right? So it's basically with respect to node V, we need to know the neighbors of V, how well are they connected to each other. Okay, so in a random graph, you can basically compute this. So how many neighbors do I have? So so this node has a certain number of neighbors. So that's actually this m. Let's see, how many neighbors do I have? Right. So this is a node with degree k. So I'm assuming that I pick a node with degree k. So I have k neighbors, and so it's going to have k choose 2 possible. So if I want to know the clustering coefficient for V, it's some number divided by k choose 2, right? Because I have k is the degree of V. So I know I basically fixed the degree because I want to know the clustering coefficient distribution with respect to the degree. So if I pick any node with degree k, it will have k choose 2, neighbors. Oh, but then the question is, what is the probability? How many edges do I expect to see? Right? Well, since every edge can appear with equally, equal likelihood, every edge has a probability of being chosen, which is p. So the number of edges I expect to see is actually just p times k choose 2. So I mean, in a random graph, it's actually extremely easy to know what is the, this is the expected. I mean, this is the expected number of neighbors I expect to see. So in this, so there are k choose 2 possible edges I could have had. Each one of those edges is present with probability p. So it's p times the number of trials I have. So that's exactly how many edges I expect to see. And so when you divide them out, it turns out to be simply P, because they basically cancel out. The number of possibilities k choose 2, the probability of success is P. So P times that is the number of edges divided by, again, k choose 2. So if you just do the math, essentially, it's easy to see that, essentially, since P is the probability of success, that essentially is also your clustering coefficient. Okay? So it's basically saying that here, your expected number of edges is just P times k choose 2. And the k choose 2 and the k choose 2 cancel out, and you're left with P. So what does that mean? That means that when n goes to infinity, right, n goes to infinity, P goes to 0, that means obviously your clustering effect is 0, right? There is no clustering effect at all. So in random graphs, we do not expect to see this, local clustering at all. So this is another key difference between a random graph and a real-world network, is that real-world networks have this clustering, whereas random graphs do not have. So that's also one issue. Now the final thing is, what about the small world behavior, right? And I said that randomness is enough to get you the small world behavior, and this we can actually easily observe by looking at okay, so this we can easily get by observing this So I want to know something about the average path length. Okay, so first we look at this, so here's a random graph, let's say, and let's start with the given node V. So what I want to know is that, okay, so for this V, we know that it has a mean, it has a mean degree, right? And that mean degree happens to be n times p, the lambda. So lambda, which is np, let's assume that this is a constant for now, and so this is your average degree. So in other words, this node is going to be connected to a certain number of nodes, lambda of them, right? Okay, but if you think about this for a minute, each of these nodes, because in a random graph, because it's a binomial distribution, it has a very well-defined mean, and the variance is also rather small. So it's a characteristic of the network. So we can use that as an approximation for the whole graph. So we can say each one of them, let's say if it's 4, then each one of them is also connected to 4 other, 3 other nodes, right? and basically you continue expanding that way. So if you look at the one hop away, how many nodes can you reach within one hop away? So one hop away, so I can do here, the number of hops and the number of nodes that I can reach, right, within that radius. So one hop away, I can reach lambda nodes, right? So those are my direct neighbors. 2 hops away, which is what I've drawn here. So 2 hops away, I can reach lambda squared neighbors, right? And so, of course, this is again a simplification, right? So it's a very coarse approximation because, it is possible that this guy doesn't introduce a node, it connects back to that. So those kind of things can happen. But, in general, if you ignore those kind of effects, and we just assume that you keep on introducing new nodes and new nodes each time, then you will see that more or less it's a good approximation because this is characteristic of the network. And so this can be done, within, let's say, t hops, you're going to reach lambda t. And essentially what this is that we can show that this is actually, so t is actually going to be log of n. Because, right, each time you're growing by a constant factor. So it's very easy to see that it only takes a logarithmic number of steps to reach the entire network. So we can easily say that the average path length is basically going to be on the order of O of log n. So that's very, so that's one of the, as I said, randomness by itself is enough to give you a small world behavior. That generally in a random graph you don't expect to see very long path lengths or diameters and those kinds of things. So, okay, this is where we are. So now we know something about the random graphs, but there are two things where it doesn't really work out, right? So it doesn't work out for the degree distribution, it doesn't work out for the clustering effect. So the next question then is how can we, basically do a model for those? Okay, so here's the explanation for the clustering effect. So how might the clustering effect happen? So this was the what Choget's small world model. So what they said is that actually, if you look at how people connect to each other, there's some sort of locality or geographic proximity is one indication how people might connect, and that will automatically give you some sort of a spatial sort of a clustering. Right? So obviously people in Delhi are more likely to connect with people in Delhi versus people in Shanghai, for example. Right? So the geographic proximity, just the fact that you might happen to meet in that city or in a smaller locality, you have more chance of getting connected versus people that are remote. So this model sort of takes that idea and says, okay, let's start with a network that that sort of models this proximity, this geographic, spatial locality or proximity. And so that's our backbone. So this network basically starts by saying that what I'm going to do first is you give me the number of nodes you want. Okay, so n will be given to you, and I put them in a ring. Okay, so the first thing I do is I connect them in a ring-like structure. So my red edges, all these 8 vertices will be connected in a ring first of all. Okay, so that becomes my backbone. Okay, so you're always connected to your left and right neighbor. In addition, what we'll do is we'll make sure that every vertex is connected to k of its neighbors on the left and k of its neighbors on the, so k on the left and k on the right. So k can be, so if k is equal to 1, you'll just get the ring back. Okay, 1 on the left, 1 on the right. But in this case, I'm showing you with k equal to 2. Okay, so you can connect with 2 neighbors on the left and 2 on the right. So you connect to V7 and V6 on one side, and V1 and V2 on the other. So 2, 2, right? So actually every degree here. So this is a very, very, uninteresting graph in that sense, that every node has exactly the same degree. The degree of every vertex is 2 times k, right? So whatever k parameter you choose, you connect it to k neighbors on the left, k on the right, and so that's 2 times k. So it's a regular graph, but these are the 2 input parameters. And you can do this in, this is like a one-dimensional layout. You can do this in, higher order, you can do 2-dimensional layouts. So if you really want to do 2-dimensional, what you do is you lay out the vertices in this manner. And now you say, it's more like, in 2 dimensions, right? Whom do you connect with? So you can say, I can connect with one neighbor on the left, one on the right, and then you can circle this back here, and you can circle this back here. So it's like I'm connected to all 4 of my neighbors, but it's more like a torus. Okay, so you basically loop around and this can be done. This is this is called a lattice. Okay, it's like a closed lattice, and this can be done in 3 dimensions, 4 dimensions, as many dimensions as you want. You can generate a graph with that property. But for us, we'll just do a simple linear. So the linear would be simply you have a bunch of nodes, which I have, right? You start with that backbone, you do the circle, and then you say how many other neighbors do you connect? Okay, how many hops away do you connect to? So that essentially boils down to this network. So this is just a 1D sort of geographic or spatial layout, but you can do 2D, 3D layouts if you want. But let's stick with the 1D. So this network, as I said, is not that interesting, but it has one key property. The property that if you study the clustering coefficient, I will not go through the whole derivation here, but if you look at the clustering coefficient, it turns out to be this very nice closed form formula. Basically, it turns out that the clustering coefficient depends on the k. Okay, how many neighbors on the left and how many neighbors on the right you connect to. And the clustering coefficient for any vertex is actually 3k over 4k. As k becomes larger and larger, so one can say that as k goes to infinity, that is, if you start connecting to many, many things on the left and the right, the maximum value of the clustering coefficient is 3 over 4. Okay, 75 or 0.75. Okay, so anyway, so there is something, but there's one key flaw. So this, our backbone has good clustering, right? As you can see, the local clustering is there, but the number of hops is extremely large, right? So to get from, just look at the, if you look at just the, excuse me. So to get from V to V4, you can either go, so you can go in steps of k, right? So I can go from V, jump to the kth neighbor, from that jump to the kth neighbor. So in this case, it will take me 2 hops, right? But in an network, it's going to be n divided by k. Okay, that's, or n by 2 divided by k, because half the nodes will be on one side. So it's like saying that in a big network, what we can do is, so let's say extremely big circle, and you start here, right? You can go in steps of k, right? So this is k hops away, 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 like that. So by the time you get here, this is half the network. So let's say there are n over 2 vertices, and you do k hops, it's basically n over 2k, right? So the distance, the diameter of the network is very large, but it takes you too many hops. I mean, it's basically k is some constant, so it's basically O of n. So that's not a real, it's not a small world network. So this, like I said, a design network like this is not very interesting from the point of view of the small world property, but it has a local clustering structure. So the question is how to fix it. So here's where the key observation comes, that actually all you have to do is, and this is the key insight, you just have to add a few random edges. Okay? And the interesting thing is that a very small fraction of random edges is enough to take a very regular graph like what we have and turn it into a small world network. So remember our backbone, this is a much larger graph, and in this case I have, I guess 3 neighbors to the left and 3 to the right. Okay, so every node has degree 6. So every node, so there is by design, there is a local clustering structure going on, and then I've just added a few more random edges. Just pick any 2 nodes and connect them, any 2 nodes and connect them. A very few of these have to be done, so the probability of adding this random edge is extremely small. And if you do that, it turns out that suddenly the network diameter shrinks. Okay, it actually goes to logarithms very quickly. So that's the beauty of this model, is that it preserves clustering, okay, and it gives you, just by random, by adding the randomness, it gives you the small world idea. But there's one problem with this. The problem is that unfortunately the degree distribution is more or less constant, right? So if I'm adding only a few of these random nodes, so let's say that really doesn't perturb the degree too much, but every node is more or less still regular. It's still, 2 times k is the degree of that. So the degree distribution is more or less constant, okay? So it's not a power law. So this model sort of fixes one issue. It says that I can get a local clustering, but it's not able to give you the power law using the sort of a design, locality preserving network. So this is sort of the flaw of this model, is that you don't get the power law. So then we move on, we say, okay, fine, how can I get the scale-free power law? And this is again a very, very influential idea. The idea in this model is that basically what we're going to do is very simple. And this process will generate the power law. Okay, and this model is also known as the rich get richer model. Okay, so what is the key idea here? This is also, by the way, the Laszlo Barabasi and Albert, they proposed this model as one of the key sort of the mechanisms by which power laws can be observed in real world networks. And this is generally true for social networks. Okay. I mean, maybe not for all, but some of them definitely this is true. And it's kind of like maybe human psychology. So the idea is that, if you, let's say I'm a newcomer, okay, so I want to join some social network, and I look at the network, right? The first thing I look at, okay, here are some of the nodes with high degree. So I'll be curious, right, to see who these guys are, and then I might go and look at their interests, what they do. So I'm kind of more likely to connect or follow, already nodes that are high degree nodes, just by the popularity sort of a context, right? So if you were to choose to follow some people, you might do that on many, for different reasons, of course. It's not just one explanation. You could have based on interest, based on, friendship, family, whatever. But sometimes you just look at the degree and you say, okay, these guys look to be very popular, I'm going to connect with them. So essentially that's kind of like the idea here that over time, the nodes that have high degree will tend to accumulate more and more connections. So the degree tends to get more and more. And that actually is a cause for power loss. So this doesn't happen too often. But once a node gets enough sort of, traction, many other nodes, start connecting to that one, and this becomes like a hub, like a power law, distribution that we want. So, and this is also known as a preferential attachment, because I can sort of now do this in terms of probabilities. So I say, if a new node wants to join the network, what is the probability that it will connect to the existing node? So it will attach to some nodes with some preference. Okay, so that's where the name preferential attachment comes from. So again, the idea is extremely simple. So let me just illustrate it, because it's easy to just see how it happens. So the idea is that we start with some sort of a seed network. Okay, so there is a N naught and there is an M naught, and normally the best thing is to choose, let's say, let's make it 3. Actually, I'm just going to start with a complete graph. Okay? Not a complete graph, sorry, a complete cycle. So let's say 3 nodes, I'm going to arrange them in a triangle. Okay? This is my starting point. You can choose bigger circles if you want. Okay, so now the question is, so this is what I'm going to call, this is the graph at time 0. Okay, so G naught is the graph at time 0. It's just a cycle or a clique, in this case it happens to be both a cycle and a clique. So let's make it a little bit more interesting. What about, so let's make it 4. Okay, so I start with 4 nodes. They are arranged in this, cycle manner. That's one choice. Basically, every node has equal degree. So initially, all the nodes have equal chance of being selected. Now, a new node comes in. Okay, so a new node comes in. And the question now is that who will this node connect to? Okay, how will I choose its neighbors? So there's another parameter. The parameter is how many nodes do you want to connect to begin with? Okay, so that's a fixed parameter. So Q is the number of neighbors. Okay, so in this case, M naught is also 4. I choose 4 edges as my starting point, 4 nodes and 4 edges. So that's like my initial state. But every time a new vertex comes in, it will connect to Q neighbors. Okay, and of course Q has to be less than N. It has to be less than N naught. So I'm just going to say, for example, let's say 2. Okay, so every time I have to select two other nodes to connect to. Initially, if you look at what you do is you look at the degree of the nodes here. So what is the degree here? Is 2, 2, 2, 2, right? We always start with a regular graph to begin with. So the probability of being chosen is basically 2 over the sum, which is 8, which is 1/4, right? So that's expected. So the probability of being chosen is 1/4 for all of them. So what you do is you compute the degree distribution at each step, and you look at the probability of of that node in terms of its degree. So in this case, I say, okay, it doesn't really matter whom I connect to, so I can just pick maybe this one and connect it. I pick that one and I connect it. Okay, so one step done. So every step, Q edges are being added. Okay, so now this becomes my G. So the graph up to this point is I've added one node. So what happens next? Okay, so a new node comes in. Okay, now things have changed, right? So once I did now the degrees have become slightly different. So if I now recompute the degrees, right? Some of them have become 3, some of them are still 2. Right? So this remains the 2, this remains the 2, this becomes the 3, this becomes the 3. So now, see, certain nodes have now bumped up the probability of being chosen in the next step. So here, This is what, 6, 10, right? So this has 30% of being chosen, 30% of being chosen, 20%, 20%. So we choose proportional to the degree. Okay, so this guy will say, it has a higher likelihood of choosing a vertex of degree 3, so maybe I choose this. But of course, it can also choose this with 20% probability, so it chooses that. And you continue this way. So every time you add q, in this case, 2 new edges, and you connect to the previous thing with a certain probability, and this becomes G2, and you repeat this whole process. So now a new one comes in, and now, I think now you see the whole rationale for this preferential attachment, right? So this node now has degree 4, this has 2, this has 3, this has 3, this has 2, this has 2. So obviously now, right, the node with the higher degree has more probability of being chosen. So it's still a probabilistic growth. We don't always choose that. But the idea is that over time, the initial nodes, they tend to accumulate more and more and higher degrees. And that's where the power law, this hub sort of node emerge from this method. So that's the basic, Barabasi-Albert model. You can do many other variations of this, but this is the key idea. So then the question is, okay, fine, now you have this thing, what are the properties of this method? So again, I'll not go through, through the whole thing, but one can, show through a variety of arguments that this Barabasi-Albert model, the BA model, or the preferential attachment model, it has a power law. Okay, it actually shows that the degree distributions are more or less proportional to k to the minus 3. So it has a slope which is kind of fixed in some sense in the way we are doing, but this can be manipulated with different, with sort of variations of the method. So that's not the key point. The point is, yes, you do see a power law. In this case, the slope is a steep slope. It has a minus 3 slope. And many real-world networks are between minus 2 and minus 3 anyway. Okay, so this is kind of like approximating maybe one explanation. Again, not a complete explanation, but it is one of the explanations. So it has this scale-free behavior. The diameter tends to be very small. Okay, one can show that the diameter, empirically one can show that this is log over log n. So it's a small world network. But unfortunately, it doesn't have clustering. So it has one, so it misses the other part. Okay, so if you look at the clustering effect is log n squared over n. Now remember, n is extremely large, and log n squared is not too big. I mean, log n squared is still kind of small. So the clustering is generally very low, even if it's a very tiny amount. So it's better than the random graph. Okay, it's not, for random graph it's pretty much 0. So here it's a little bit better, but it's still extremely small. So you don't expect to see too much, clustering. So then my final model, which I'm going to discuss, and then that'll be our the first part of this lecture, is what about other models, right? So there are many other models. I'm not going to go through all of them. So people have suggested various mechanisms, right? So how do real networks evolve? So there is an example, what is known as a model. So what they say is that, if you, and this is kind of, maybe inspired by the web. So let's say you want to make a new web page, right? And the web page is on, I don't know, data mining. So how would you make that web page? I mean, you can do all the effort, you can do a lot of research and, come up with a brand new, organization and scheme. Or what you can do is you can go to maybe your favorite websites, maybe 2 or 3 of those, and you can borrow some key ideas from those, maybe as a template. So they say that normally what happens, I mean, this is kind of like a model to capture that kind of behavior, that you have a graph G, okay, this is already there, and this graph has certain, properties. So if you want to create a new node, the idea is that you randomly pick one node, let's say I pick this node, and you sort of replicate its connections, right? So if you want to make a new web page, maybe you start with some existing framework, borrow all the links, and then you change, you make your changes. So the idea is that you replicate this kind of a structure. So that means this new node will also be, it will just copy the connections from here. So it will connect to that, it will connect to that, it will connect to that. Right? So whatever this node was connected to, you, and this one node. Right? So you start with those, you replicate. Essentially it's a copying model, it's an edge copy model. And then you can throw in some randomness. You say, okay, after I've copied this, I can randomly remove that. I can maybe randomly remove this, and maybe I can randomly add some other edge, right? So you can do some sort of randomization because you don't want to blindly do the same thing each time. But then what about this model? What are the properties of this? So people have studied, if you do a copying model, what kind of behavior emerges from that? And this also tends to, I'm not exactly sure, I think it's, does it have all three properties? I don't think so. Maybe the clustering effect is not there or something like that. So that's one of the models. Another model that I want to mention, which is actually also very powerful, which I think tends to capture a lot of the properties, maybe all three of them, depending on the parameters you choose. It's called the Kronecker graph model. And so this is a model that will actually have all three properties in one of the models. I mean, there are probably other models one can have, but this is a nice model because it is sort of a generalization of many other models. So it has a small world, it has clustering, it has power laws. So it has at least those three properties. Some other property you might be interested, it may not have, but these three main ones it has. So what is the idea here? The idea here is actually recursive, like a fractal growth. Okay, so we start with a very small seed, and we basically grow the network from that seed. So let me show you an example. So let's say I start out with a network like this. Okay, so here's the network. In this case, I'm also adding a self loop. Okay, so every node is connected to itself. What is the adjacency matrix for this network? Okay, so it's going to be a 3 by 3 matrix. So this is node 1, this is node 2, this is node 3. So 1 is connected to itself, it's connected to 2, so it will be something like this. 2 is connected to everyone, and 3 is connected to this, right? So this becomes your seed. Okay, so I'm going to start with the seed matrix. Okay, but now comes the Kronecker multiplication. Okay, so Kronecker multiplication basically is this new operator, where what you do is, so basically this is a graph, right? So let's just call this G1. Okay, G1. So G1, you sort of do a self-replication, and instead of writing the actual mathematical form, the idea is that every place where you see a 1, you put a copy of the same graph. Okay, so the next level is the entire matrix will be put in. Whenever you see a 1, the whole graph will be replicated in that spot. And if you see a 0, you don't do anything. So the idea is that from here, I mean, it's going to be extremely hard for me to do this, but let me see if I can do it. I think it's not too hard. Okay, so the idea is that you make a new, much larger matrix. Okay. This matrix is actually just a copy of this. Okay. So whenever you see a 1, you copy the whole graph into that spot. There's a 1 here, so you copy again the whole graph. So actually I could have just written it this way. G1, G1, 0, G1, 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 G1. So this is called G2. So, and G2 is the Kronecker multiplication of the graph with itself. Okay, so G2 is G1 Kronecker multiplication G1. So you see what happened is that I replaced the whole graph there. So it's a fractal process, right? So no matter which scale I look at it, the graph looks exactly the same. And you keep on doing this for many, many steps. So you can bigger and bigger. So exponentially you expand the number of nodes in the network. So you can generate very large networks very quickly. so I'll just finish this one. So this one looks like this. And this, of course, is all zeros. Okay, whatever this graph turns out to be, essentially it's a self-replicating and it's a fractal process. And then you repeat this for many steps. So keep on doing multiplication all the way up to GK. So now whenever you see G1, here in G2 you keep on replacing copies of G2, then copies of G3. So it's a basically it's a fractal process. Okay, now this graph is of course extremely irregular in that sense because you start with a template, okay, and you keep on replicating that template each and every time. So this will have certain degree distribution, and they show that they happen to be multinomial distributions. So they're not exactly power laws. Now there's a way to make them power laws, and the idea there is that instead of starting with just 0, 1, you put a probability of an edge. Okay, so you follow the same basic principle, but the idea is that you instead of starting with just zeros and ones, we start with a template in a G1. We say that, so in this small example that I have, maybe we say the probability of a self loop is 0.5, probability of this edge is 0.7, probability of this is 0.1, probability of this is 0.3, and the probability of this loop is 0.9. So the idea is that you add confidence or a probability of that edge being present. Okay, so now you get the same Kronecker sort of idea. You're going to get 0.5, 0.7, 0.7, 0.1, 0.3, and 0.3, 0.9. So you get a template. And now what happens is you follow the same Kronecker idea, but now the next probability. So this is basically a G1, right? So now what is the expansion to the next step? Well, it's a new graph. Each one of them, as we know, is a copy of G1, right? But there's a key difference. The key difference is that all the probabilities here will be multiplied by 0.5. Okay, so take G1 and you multiply it with the, right, so first you make a copy of the graph in some sense, and then you multiply everything there. So it's actually 0.5 times G1, okay? And this would be 0.7 times G1, you see? So the probabilities will now get propagated as you grow the network. Okay. And then essentially the idea that if you want a random instance, you can simply sample from this graph. Right? So now you have the probability of each edge, and you can simply sample from that, and you can generate a random network. And what they show is that depending on your starter matrix, so essentially everything boils down to how you start. And what they show is that actually for many real-world networks, they can start with different probabilities, and then those lead to power laws, they lead to clustering effects and things. Okay? So you have to sort of start with the right set of parameters. So it all basically boils down to that if we have a real-world network and you want to generate a synthetic network like the real world, simply you have to do a reverse engineering. Figure out what your starting graph should look like. And then this Kronecker process is able to replicate lots of these properties. So this is a very, very powerful model for analyzing these networks. So, and you can see kind of like why it preserves, so if the initial graph has clustering, that clustering, stays on for the remaining. The power laws can be modeled by having high probability, edges, and so those power laws, so those hub nodes will emerge as you replicate the network more and more times. So those probabilities will still remain high. And the diameter by design is not that large to begin with, because exponentially you reach pretty much the whole network. So it's only a logarithmic number of steps it takes you to reach the whole network. So it's a small diameter or small average path length. All right, so that's essentially what I wanted to say about this part of the lecture, of the topic. So that essentially is just sort of analyzing graphs from a structural point of view. Okay, so we're going to take a quick break for 5 minutes, and then we'll go on to the next part, which is pattern mining. So in the next part, I'm going to talk about this.